Okay, good afternoon. Welcome to the Renewable Energy and Sustainability Systems Graduate Seminar here at Penn State. This seminar series is part of Penn State's online master's program in renewable energy and sustainability systems, offering graduate instruction in the areas of bioenergy, solar energy, sustainability management and policy, and wind energy. My name is Daniel Chokas. I'm the academic program coordinator of this program, and it's my pleasure to welcome you here today. The seminar is being delivered on campus as well as online. After the presentation, we will have time for questions and discussion. Those of you who are here on campus, of course, will be able to ask your questions directly of the speaker, but online attendees, please type your questions in the chat window that is part of the meeting software package. Today's seminar will be given by Dr. Richard Flarin, Associate Professor of Physics at Penn State Altoona. Dr. Flarin teaches physics and energy and the environment. His research interests include solar energy and incorporating renewable energy with other energy systems. Current projects include seasonal storage of solar thermal energy and water cooling applications for photovoltaics. Now, his topic for today, however, is solar energy utility profit margins and consumer savings. This is something that has been the subject of recent discussion and perhaps even controversy in the state of Pennsylvania, and it's very relevant to the sustainable development of our energy resources. Dr. Flarin.
Thank you. Well, thank you, everyone. I am going to talk about net metering and how net metering actually impacts the bottom line of utilities as well as generation suppliers. And so to get started, let me just show you where I studied. This is the entire state utility district, broken up into all the different utility districts. I chose the Duquesne area and the Petco area, so the blue over here and then the light purple over there. And I studied 2 years of data for 2012 and 2013, all of those years. And we basically broke down by hour what the demands were, how much electricity was produced in those areas, how much electricity was needed. I looked at all the solar arrays that we could find that were publicly available to see what they actually generated during those times, and then analyzed all that data to figure out what the net profit was to the utilities. So to give you an idea, we are in Pennsylvania. It's a fairly cloudy area, so we can see that in that map. People think of this as not a very good solar area, and this shows the data that I was actually collecting. This is using Enphase Enlighten. This is a commercially available software that monitors inverters that homeowners and business owners who have solar installed, how they monitor their system. This shows a complete year of data. Each row is a month, and then it shows first day, second day, and so forth in the month. And what you see is that indeed during the summer, these boxes are a little bit lighter. They're color-coded based on how much energy is generated. And so you'll see more energy is generated on this day. This day is really bad. Not very much energy is generated. And so, we do get energy that fluctuates from day to day throughout there. On the other side, you'll see kind of a split screen here. This is a map of the Pittsburgh area, and everywhere where you see these dots, those are solar arrays, and then these blue things, actually you have to click in and explode that area to see many more arrays that are right in that particular spot. The Pittsburgh area, there weren't a whole lot of solar arrays. There were only about 35 solar arrays that I could monitor, but I chose Pittsburgh to get started with because it actually was a relatively small utility district, and collecting the data was a little more manageable. And then we moved on to a much larger area in Pittsburgh where we were, in Philadelphia, where we analyzed over 100 systems. Using this, and then collecting the data, when you click on one of these, then it changes the graph from a graph of the entire month. It changes to a graph of a particular day. And then it gives you 15-minute interval data on solar production. So we had to collect all that data and analyze it, which actually required a lot of basically data mining of the web. So we had to write computer programs that would mine the data from the web to collect all this so we could use it. So the first result is that forward does not equal backwards. Net metering is the idea. Here's a graph that shows the general idea, is that the top line shows the graph, or shows the energy demand by a particular consumer. That shows the price. This line shows the demand by a particular consumer. The dotted line shows what the demand is after they have solar energy producing part of their energy. So at nighttime, they don't have any solar energy, so their demand is what they actually need. During the daytime, they produce some of their own energy, so this is actually feeding the grid back they're getting credit from the utility for this. And then during later on during the day, the sun starts to go down. It gets later in the day. They're still producing energy, so their net demand is less than what their total demand was, but they're still buying energy from the utility company at this point. And so they get a credit for all of this. They get billed for all of this, and then the net bill is basically the difference between what they used and what they got credit for. I actually call this deposited energy, because you think about net metering, it's literally just like a bank account. When you spin your meter backwards, you get a credit from the utility company for that. And that's the same thing as depositing money in the bank. And then you withdraw money from the bank. And whether your bank deposit or your bank balance goes up or down depends on the difference between those two numbers, whether you deposited more energy or whether you withdrew more energy. And so the first thing to analyze was, what is the value of this energy that is feeding the meter backwards? What is the value of this energy, which is feeding the meter forwards, that you're actually drawing from the utility company? And the net result was, over the course of 2 years, between these two different utility companies, in 2013, there were a total of 6,000 kilowatt hours that were deposited and then withdrawn. Now, this isn't by accident. These two numbers were the same. We actually don't know for a particular user. We can figure out how much energy they generated with solar, but we actually don't know on an hourly basis how much energy they drew from the grid. So one of the premises that I made in this research was to assume that a particular user had a system that was perfectly sized for their house. It generated exactly the amount of energy that they used on a yearly basis, and that how they used the energy through the year and through the day on an hourly basis was the same as the aggregate of all customers in that utility district. And so based on that assumption, we were able to figure out that the average price of electricity that they deposit on the grid was 3.9 cents per kilowatt hour, and the average price of energy that they drew from the grid that they would actually pay for, that the utility company is providing, was 3.4 cents per kilowatt hour. The difference is, of course, what they deposited was 16% more valuable than what they used from the utility. Now, this particular user, by definition of the way we did the simulation, is actually not going to pay the utility anything. So they're going to have a zero bill, but what the utility company gets out of this is they get electricity that is more valuable that the user is giving them than what they're providing to the user at nighttime. Basically, daytime energy, if we simplify this, daytime energy is more valuable than nighttime energy. And so we can see that. We saw the same thing in the Petco area, which is Philadelphia. And then we look over here in the next year for 2014, you'll see the exact opposite going on. You'll see that the nighttime energy was actually more valuable than the daytime energy. And so in that situation, that would represent the utility company literally losing money through the net metering process, that the energy they're giving back is more valuable than the energy they're getting during the daytime. We looked into why that was, because that really seemed puzzling. And there were also some other things that when we looked at those particular years that I'll show you a graph later on, where it just immediately pops out that something really weird was going on. So I started looking more carefully into the particular hours where this electricity was so valuable at nighttime. And we found out that it was limited to two particular months. It was limited to January and February, and they were all on basically really cold days. And so this just shows what the average temperature was across the entire world in January 2014. And you'll see that it was really a rather cold January in the Northeast. 2015 was even colder, and so we haven't run the data for 2015, but I fully expect to see the exact same results for 2015 because of that extreme cold weather. And this wasn't extreme cold weather. It turns out that if we plot the number of record high temperatures that were set or record low temperatures that were set, there was, and you plot that every given year. So in 2000, how many record low temperatures were set in the month of January in Pennsylvania? It's really easy to pull up data like that from the Weather Service. How many record low temperatures were set across Pennsylvania in January of 2011 and then 2012 and so forth. You'll find that typically throughout all of Pennsylvania, we'll set something like 10 record low temperatures across the entire state. On those particular months, we were setting something like 100 record low temperatures across the entire state in that particular month. So these were indeed record low temperatures. I don't have the information to show here, but the U.S. Department of Energy actually sent out a daily bulletin And they actually sent out a bulletin in 2015 actually pointing to this effect and actually showing that because of the record low temperatures, natural gas prices were climbing through the roof, really unusually that it was happening right in January and February. And so basically because that was increasing natural gas prices for heating, then because we're getting a lot of electricity from natural gas now, that was increasing the price of natural gas powered electricity. So what I then decided to do was, well, let's just look at March through December. Let's take out the extreme cold weather month. And if you remove the extreme cold weather months, then you actually get more or less identical data between 2013 and 2014. Now the deposited kilowatt hours and the withdrawn kilowatt hours are not the same because we're removing, several months worth of data here. But in terms, the price ends up being more or less the same. And there's a lot to be said about this in addition to whether this is actually a fair thing to do or not. Most people who have solar do not have a solar array that's big enough to power all of their electricity. Most houses just don't have the roof space to do that. And most homeowners don't have the budget to build a system that large. And so, so the whole premise that we were saying that the solar array was going to generate the exact same number of kilowatt hours as they used, that's probably not actually a very appropriate a model because that would very rarely actually happen. And so this is actually a more appropriate model in the fact that they're going to, basically at this time, they're going to use less energy. They're going to generate less energy from solar than what they actually use. And if you look at the way most of the utilities around here work, West Penn Power, Penn Electric, Petco, throughout all of Pennsylvania, the utilities work on a budget year that starts in the spring and goes all the way through to the next spring. So most people have solar energy and they net meter. They run their net meter balance and they basically don't pay bills up until some point in the fall, maybe December, maybe November, maybe if they're lucky January. And then most of the time, they actually are paying bills during January, February, and March. And so this is actually probably the way that the data should be run after the fact, after we really started studying this, because this is what is probably mimicked by most residential solar users. So anyway, the net result here is forward does not equal backwards. In a normal weather year where we don't have record low temperatures, the utility will actually gain about $50 per year per customer. And the idea that they actually have, increased costs is actually the other way around. They actually have increased gains because of the solar energy. So if anything, they should pass those savings along, or they can use those savings to perhaps upgrade the grid or something like that. So the next big point that I would make is intermittent does not mean unpredictable. We all hear about solar and wind, renewable energies being intermittent, and that's absolutely true. And sometimes people will talk about that as being equivalent to unpredictable, and that's absolutely not true. So I put a little byline on here, is that if you knew how the stock market was going to behave 24 hours in advance, how much money can you make? You could make a ton of money, right? In fact, the answer is, well, how many trades can you actually make in that 24 hours? Because every trade you make is going to be very profitable. So your profit's going to be limited to how much trading you can actually do during those 24 hours. Well, I say that because the utility, the way that we buy electricity is a trading mechanism. Utility companies or suppliers go and they bid for electricity, and power plants are offering that. And so there's a market that is every day there is a 24-hour in advance bid process that happens. And if they know what's going to be going on in those next 24 hours, people can use that to their advantage to basically make more informed bids and make more money that way. So here is kind of a graph on the bottom. So this basically leads into what market suppression of electricity rates is about. And on the bottom here is a graph. This is the PGM network, the entire Northeast. The graph in the background, which is this blue, the lighter blue, is, and this, by the way, was in November. This was, I don't remember what day, but this was a particular day in November of last year. And the blue in the background shows 24 hours in advance what the prediction was for all of the wind energy and all of the PGM network. So this is all of Pennsylvania, all of Maryland, Virginia, go down all the way to North Carolina, all the way west to parts of Illinois. And so you'll see that, the wind energy was going to start out relatively high at midnight go up a little bit more. It's going to go down during the day, maybe peak a little bit in the afternoon. Some afternoon breezes come by, go down, and then go way up toward the next day. So maybe this is a storm front coming through. I don't really know. And by the way, you can actually go and see this graph at the PGM website each day. So today you can go on there and find this graph, and you'll see the prediction as of last night, and then you'll see the graph up until right about here with how well has today's actual production matched the prediction from the day before. And by and large, the prediction always mimics the actual production always mimics what the actual prediction was 24 hours in advance. And that's not, by mistake, because PGM, utility companies, they spend a lot of money on getting really good weather forecasts, and they get good forecast models because this is about money. They take this prediction and they use this prediction to bid intelligently on how much they should pay for electricity for the next day. If they didn't have this prediction and they bid for a certain amount of power right at this particular point, and then all of a sudden the weather is producing a whole lot of wind energy, that wind energy is going to supply too much energy to the market, and suddenly they would find that they would have bought too much electricity from the hours from 10 p.m. to midnight. And then they'd be having to offload all that power in basically the real-time hourly market, and they would take a big hit for that. So basically they use this to bid intelligently. There is the same type of forecast that happens with cloud cover, which basically translates into solar energy. And so this is a cloud cover. This is actually publicly available, where you can pull up the tomorrow's forecast of cloud cover. And you can click up here to actually, look at particular hours. So this is not just, the cloud cover at one particular point. Clouds move around. This is at the time from 2 to 3 p.m. And then you can go back to 11 and look at what 11 to 2 p.m. is. If you're willing to pay for it and get a proprietary weather forecast, then you can get this in like a moving video stream, and you can get what the weather forecast is, or the cloud cover forecast every 15 minutes for the next day. And if you're willing to pay for it, you can also get this updated every hour during the day. So it's constantly being updated. There are people who do that pay for this. I was down at Charlotte this last year and was able to tour the Duke Energy Renewable Energy Command Center, where they actually do the command and control for many of the solar arrays and wind farms that are throughout the entire nation. And they have these type of weather forecasts up and running, being updated constantly through the day. And indeed, what they say is that the predictions for cloud cover for solar are far more predictable than the predictions for wind energy. And you saw how predictable the wind energy was. They actually say the wind energy is not that predictable compared to solar, and that solar is far more predictable. So that's actually something rather interesting. So with that in mind, this is the price per megawatt of basically, it looks at the price per load throughout the two utility districts. So this is Pittsburgh 2013, Pittsburgh 2014, Philadelphia 2013, Philadelphia 2014. Let me tell you the graph that I was indicating, that right away we knew something really was weird about 2014 with the cold weather. This is a graph. You get a graph like this when you pull up, you make this graph for any year, any utility district. That's a classic graph. It says that at low loads, your price is low. At high loads, your price goes exponential. And there's some scatter in there because, it's more than just how big the load is. It's also how big the load is, how long it's been high. So if it's been high for 4 days, straight, that's going to push the prices even higher. And in which case, if it's been high for 4 days, it doesn't even have to get all that high for the price to go, rapidly upwards. So there's some things that scatter the graph up here. So it's kind of a messy thing. You can't just fit this to a trend line. But it shouldn't look like this. This is really crazy. And this shows that, you can get a really high load, and the price is not very high. I mean, actually, this price, the scale is different. That goes up to $350, and this goes up to $1,000. So here the price goes up to maybe about $150 per megawatt hour. But somewhere in here where we have moderate loads, only 2,000 megawatts, the price goes up almost to $1,000 per megawatt hour. $1,000 is an outrageous price. That's $1, translate that into what you pay for electricity as a consumer. That's $1 per kilowatt hour. That's way more than what you pay on your bills. So these are really high rates that are peaking. And each one of these was on a record cold night or a record cold day, sometime when the temperature in January, February we're hitting record low temperature. Same thing right here in Philadelphia. It looks like there's a whole bunch of dots here, but every one of these high dots were within those 2 months, were in either January or February when we had cold temperatures. So by and large, most of the dots are down here. It just doesn't necessarily show right here. Well, anyway, this is the classic price based on demand. So if we take this and we look at and we want to model, well, what happens to demand? If we can have solar energy, and solar energy can push that demand down by basically, usually we get high demands on summer days when we need lots of air conditioning, and that's when solar energy is working really well. So solar energy can knock the demand down and produce some of that really expensive electricity, then what does that do to the price? And we can't model that with a trend line, so we have to come up with a different way to model it. So what I did to model this was I basically created a histogram or a bin analysis of this, and I basically counted up how many hours during the year was the load somewhere between 2,500 and 2,600 megawatts. How many hours during the year was the load between 26 and 2,700 megawatts, and then 27 and 2,800 megawatts. So I broke all these loads into 100 megawatt bins and counted how many hours each bin occurred. So basically a histogram. And then I took all of those hours where the load was somewhere between 25 and 2,600, and then figured out, well, what's the average price? And so this is the average price that's plotted with these white bars, and these white bars give the average price, and you'll see that the average price is really low for low loads, which is what we would expect. And as the load gets higher, the price goes up. And indeed, at this point, this really is looking like an exponential. And so that's kind of what we would expect. Something else that we see is that the noise when we get to these high loads, there was quite a bit of noise you saw in those previous graphs. So I also plotted the error in the average. So this is not standard deviation, but it's the standard error in the mean. And so I plotted the standard error in the mean. And so we have an idea of how much variance we actually have in those prices. So yes, the price goes up, but the errors actually are manageable. Those are not radically big errors. This is what would happen right now. This is literally the current situation where we have less than 1% of solar energy in Pennsylvania. In fact, we only our current solar fraction is, and the people on the internet can't see that, but the current solar fraction in Pennsylvania right now is 0.15%. So much less than 1% that this graph is showing. Well, now what we did is, let's take all that solar energy and let's multiply it by basically 100. Let's ramp it up radically and say, what would happen to this graph if suddenly we had a whole bunch more energy dumped on the market? And if we had a whole bunch more energy dumped on the market and we went up to a 5% solar RPS, which, by the way, we won't reach a 5% solar RPS in Pennsylvania for another 10 to 15 years. And that's assuming we have more or less a continued exponential growth in solar energy. So we are a long way away from this particular level of solar. We'll see more or less the same thing. I mean, the price will go up exponentially with the load, but if you looked very carefully, and I'm going to go back and forth between these two screens, look at the histogram of how many hours we see, a load from 1,500 to 1,600. So that right now is the most common load that we run into if we have a 5% solar RPS. And so it happens 250, 260 times. I'm going to go back a screen, and that particular load with less solar only happens 220 times per year, right? So we basically are pushing the peak of this histogram left, go forward, pushes it left, go back, it pushes it forward. So basically we can see the shift being pushed to the left, meaning that we're suppressing the number of hours that we're running at higher loads. Those higher loads have higher prices. So basically what we're doing is it's not a whole lot, where the prices that we're seeing are, maybe at 2,000. In fact, right now the peak is at 15 or 1,600 with solar. Without solar, the peak load is more than about 1,700. That's the most frequent load that we see. And so that most frequent load only decreased about 200 megawatts. But more importantly, the price at that point, the price at 1,700 is maybe, it's kind of hard, I don't have numbers here, but reading the graph, that's probably about $35 per megawatt hour. And going back, whoops, After the solar, the peak goes down to here, maybe it just goes down to 30. So we're only decreasing the price per megawatt hour by about $5 during those peak hours, during the most frequent hours that we actually see. We're not really changing too much these peak hours over here. By and large, those peak hours happen during summer evenings. And usually that's close to sunset or getting close to sunset. So the amount of solar energy that we get during those extreme peak hours is minimal. But what we're doing is we're impacting the bulk of the energy purchases right in here. And by impacting the bulk of the energy purchases, we make electricity cheaper for everybody. So at this point, I'm going to switch to the simulation that I have ready for y'all. And I'm not sure how this is going to work for our internet users. But you have a card that I gave you, a sheet of paper, and we're going to basically see how this works on the bidding process. So we're going to take like a typical day. I've really oversimplified this to illustrate, by the way, it is based on July 27th of 2013 for Pittsburgh. So it's based on a real day in a real city using real prices. So, but it's kind of also grossly oversimplified. And so from midnight to 6 a.m., we need, and I think this is being shared, right? Okay, this is being shared. So from midnight to 6 a.m., that's, let me delete this. I apologize for this not looking a little bit better. We need a total of 2,000 megawatt hours of electricity. So that 2,000 megawatt hours of electricity. So we're going to do a quick bid real quick. I want you to say, low bid starts off, right? So who's bidding $25? And you're providing how many? 4. Well, we need more than that. So we're going to go up to, let's say $30. Anybody bidding less than $30? Raise your hand. Okay. 26 and 28 and then that one, well, that's only 3, so we still need more. So $35. I know what the number is. So $40. Anyone bidding $40 or less? Raise your hand. Yeah, I know. So so you are. All right. So how many? Raise your hand again if you're bidding $40 or less. So 1, 2, 3, 4, and 5. Right? So that's 5 people bidding. All of you have a power plant that's producing 400 megawatts. So that's the winning bid. We now have met our 2,000 megawatt hour demand that we need. And the highest of all the bids was $40, right? So even though you were willing to bid 25, you're going to sell it for 40 because that's how the bid works, right? So you're going to make a lot of money, right? So the winning bid was $40. So that's this. So we need 2,000 megawatts at $40 a piece, which means the utility company or the supplier, whoever the supplier of energy is in this area, is going to have to spend $80,000 for that particular hour, and that's $80,000 per hour to provide that energy, right? And then we go and do the next time. So now we're from noon to 6, people are waking up, we need a little bit more power, and now we need another 400 megawatts. So above 40, let's see, someone has 60, I think. Okay, was anyone between 40 and 60? I don't think so. You have, 50 and 60. Okay, so now, are they 200 though? Yes. Oh, so we need both of your bids. All right, so now the winning bid is $60. So now we have enough energy, but we have to bid $60 at this point. So now we have 2,400 megawatt hours, and the winning bid is at 60. The total price for all that's going to be $144. And then from noon to 6 p.m., the demand goes up to 2,800 megawatt hours. That's starting to get pretty high, actually. Remember, this wasn't in July. This was a really, a high demand day. And now we need 2,800 megawatt hours. And at this point, all of you are going to have to bid, right? And so we're going to have to, everyone has to bid, and then all of you added up together are going to give us 2,800 megawatt hours. And the highest bid is, I think you had it. Yeah, 120. You're barely going to make the money you need to run your power plant. Everyone else is just going to make tons of money. Now, of course, that's actually factored into their model. Okay, so they kind of know that ahead of time. So now everyone's going to get up to $120 per megawatt hour, not just you, everybody. And so the total cost to pay for all that power is going to be $336,000. And then after that, the load goes down a little bit. And then the winning bid is only $75. Y'all see how that bidding works? Yes? All right. Well, now we go and we do this with solar energy. And with solar energy, and this is just, this is actually a reasonably high level of solar energy. This is not how much solar energy exists in Pittsburgh right now. This would be for a relatively large amount. Then solar energy is not going to do anything from midnight to 6 a.m. because the sun's not up yet. From 6 to noon, we're going to get a pretty good amount of solar energy. From noon to 6 p.m., we'll actually get more than that because it tends to be shifted in the afternoon more than the morning. And so we'll have 400 megawatt hours generated in the morning hours, 600 in the afternoon hours. And then from 6 p.m. to midnight, y'all know the sun goes down at 8:30 or 9 o'clock in the summer, right? So we still get plenty of sunlight after 6. So we're still generating some power after solar energy after 6. And so we get 200 megawatts. So that decreases our load of how much energy we need. The morning is still the same. It's still that same 2,000 megawatts. And so it's going to cost the same $80,000 that it cost before. It's the same amount now. Well, now when people bid, you're still bidding based on how much it costs for your power plant to operate. But now we don't need as many power plants to operate because now we have, on this particular day, we have solar energy kicking in. And so instead of needing from noon to 6 a.m. to noon, instead of needing 2,400 megawatts, we only need 2,000 megawatts. That's the same as we needed in the middle of the night. So the cost is going to be the same, $80,000. So right there, we saved just in that small amount. We basically got rid of whoever was bidding that 400 megawatts, and that decreased the bid from $60 down to $40. But that saved the utility company $66,000 just per hour during that amount of time. And then we go from noon to 6, and instead of 2,800 megawatts, now we only need 2,200 megawatts. And so that changes the winning bid from $120 down to $50. So this has several effects. One is that your power plant that was $120, you're not going to be in business anymore, right? But the reason your power plant was $120 is it's relatively old, relatively inefficient, and it's a lot of maintenance to operate. So this is actually kind of a good thing because the expensive power plants tend to be the older power plants that are expensive to run for a reason. And that's because they have high maintenance costs, they have high pollution control costs, and they're just really difficult to keep them running and to keep them operating. That's why the costs are high. The cheaper power plants, which are the ones which are basically newer power plants, more efficient power plants, they can produce lots of energy burning small amounts of fuel, and they don't need to worry too much about their emissions because they're fundamentally cleaner power plants. Those tend to bid in at lower prices. So what we see with this simulation is that when we have this market suppression, it saves the utility company. On this particular day, it would save the utility company on average per day, or I guess for a reasonable way to say it, $330,000. That's a huge amount of money. I mean, that's almost half, right? We went from $755,000 to purchase that energy down to $400,000 to purchase that energy. That's almost half. But if you look at these numbers, we add up these numbers here, we add them up, and that's 1,200. We add up the numbers over here, and that's over 1,000. We're only producing about 10% of our energy using solar energy on that particular day. And yet that 10% of solar energy is going to cut the cost to the utility by half or close to half, which is a huge amount of savings. All right, so let me go back to the PowerPoint. There we go. So here's what a 10% solar RPS would do. RPS is Renewable Portfolio Standard. So that basically says we have 10% of solar of all the energy we're using comes from solar energy. The impact for 2014 in the Petco area alone, this is just Philadelphia, means that the purchased megawatt hours that the utility and I'm going to clarify this a little bit later, it's not just the utility. It's also all the various independent suppliers that when you go and shop for your energy, you go to like PA Power Switch and choose your own supplier. It's all those suppliers and the utility, all right? So all those people together. The energy they have to buy goes from 40 million megawatt hours down to 36 million megawatt hours. Well, that's the 10% solar RPS. They lose 10% because we're now having solar energy produce 10% of all that power. But the cost to purchase all that generation goes down from 2.34 billion down to 1.75 billion. That's a huge decrease in cost. That's a
about a 25% decrease in cost, even though they're only losing 10% of their customers. So they lose 10% of their customers, but they save 25% on their cost. That basically increases their profit margin, which is really fascinating that they can lose customers and increase their profit margin at the same time, and their profitability, both profit margin and profitability. All right, so the net savings for generation, this is from the generation, the independent suppliers, they're going to save $600 million, but they lose some distribution costs because they're not only are they not selling electricity to the solar customers, they're not collecting distribution costs to the solar customers anymore. You'll hear utilities talk about, utility companies don't actually sell power, they sell distribution. And so you'll hear utility companies talk about where we're losing our distribution costs. We have to pay to deliver power, we have to pay to maintain the power lines, but we're not actually getting, paid for this. So this is the money that pays for maintaining those power lines. They would lose, $100 to $240 million or so, which normally would go to maintain power lines. But at the same time, they're saving $600 million. If it's the same person saving this money and not having this as income, that's really great. That means that their net benefit is, $400 million or so, about $400 million. That's really great. Incidentally, I will go ahead and say one other thing about the lost distribution charges is residential customers who have solar energy under this model would pay nothing for distribution charges. They literally, utility company loses all of that. Business solar customers actually pay the full amount for their distribution charge. So they actually, there's a little bit that happens just from second order effects, but for the most part, they're going to pay the same distribution charge that they paid before. And most solar at this point is happening at the commercial level or the utility level, not at the residential level. So that's why this range is so large. It depends on how much of the solar is residential versus commercial or industrial. So the net result here is the benefits of solar energy to the utility and to the industry are 2 to 5 times the cost. This does not include the lost revenue to power plants. Point of view, you had that power plant running, bidding at 120, you're just out of business. I mean, you're literally out of business. But that's the way of buggy whips. I kind of say that's the way of buggy whips. We have a new player in town and they're competing, and that's what free market is all about. So we can't necessarily draw any conclusions on that. Obviously there will be winners and losers. And the losers with solar energy are power plants that are expensive to operate. But they're losers to almost anything. I mean, anything that comes in and can generate power cheaper or more reliably is going to put them out of business. This shows not just Petco, not just Philadelphia for 2014, but it shows both utility districts for both years that as you increase the solar RPS from 1% or this is 0.5%, 1%, and you keep on running all the way up to 10%, you have an oversized savings of the electricity. So if you have a 10% RPS over here, you end up having a net savings in the industry of about 15%. So you lose 10% of your customers, but your net, profit margin goes up by 15%. If you lose 2% of your customers, you're going to have a net increase of 5% in your profit margin. So you basically, your savings are much larger than your cost. So now let's talk about who actually receives these savings. In the traditional old regulated market, so not the deregulated market, in the regulated market, we had member-owned utilities, we had municipal-owned utilities, and we had those big, industrial utilities. They received the market suppression savings. That's the savings I was just talking about. They received the arbitrage savings, which is maybe the $50 per customer that we talked about. They lose some revenue from distribution losses, and they also bear the burden of maintaining the power lines and actually adapting to even more solar in the future, because as we go above 10% solar RPS, we have some serious problems with maintaining the grid, and there's going to have to be some grid infrastructure to do that. So they would have the burden of doing that. But nevertheless, the cost of this is much less than the gains received there. So the net result is the savings are much, much larger than the cost, much larger by at least a factor of 2. Where are those? Well, basically at this point, the only people who fall into that category are rural co-ops. And here's a map of where the rural co-ops are. Many of these rural co-ops are very pro-solar. They see these savings. They see this actually happening, and they do lots of things to promote solar. Can't necessarily say that's true of all of them, but many of them it is. If we look at in the deregulated market for the rest of us who are dealing with for-profit industries, so the deregulated market deals with generators. I'm not going to talk about them because those are the owners of the power plants. They clearly don't like any competition in the area because it cuts down on what they sell. So they definitely, take a hit. Suppliers, utilities, and customers. Those are the rest of the regular industry. Suppliers benefit the most because those are the people literally buying on the market. They're the people who are going to receive all of those market suppression savings. They're going to save a huge amount of money. Utilities, if they can receive that market suppression, then they really like solar energy, but they also lose the distribution payment. So the question is, can utilities receive enough savings from market suppression to offset the distribution losses that they receive? The answer is maybe not, actually. And let me understand why. I'll show you a graphic next that understands why that's probably the case. Customers, these are all customers, Customers who have solar energy clearly like solar energy because they chose it. They're not paying bills anymore. But all their neighbors also like solar energy. They don't even know it because the 5% of people who get solar energy, if we had 5% of solar energy out there, then that would decrease the price across the entire market by 10% for everybody else. So someone having solar energy saves money for everybody on their block, and everyone on their block just doesn't even know it. They just don't know that the price they'd be paying without solar would be higher than the price they are paying right now. They just don't realize that. So why is I'm switching over to PA Power Switch, and the zip code in State College. What is the zip code here? What? 16801. 16801. All right. I'm going to check we're going to see why utilities don't really receive all the savings, all the market suppression savings. So I typed in our zip code here, and it says there's 83 results. So consumers around here can choose from 83 different suppliers for their energy. Well, let's just imagine that it's more or less of an even distribution with that, basically, we'll say rounded off to 100 suppliers, that 1% go with each one of those 80 suppliers or something like that. All right, so it's an even distribution. So that means that the utility company is only servicing a very small percentage of all the customers around here. And so they would receive only a small percentage of that market suppression, maybe only about 1% or 1/80th of that market suppression value. All those other suppliers, they each they each receive 1/80th of that savings. Well, now I'm going to have to go and filter this. If you have solar energy, you need a supplier who offers net metering. If they don't offer net metering, you can't use that supplier. And when we do that, it turns out you have one choice. You can go with the default service provider, which is West Penn Power, or you can go with just this one. This is the only company available to you. And it seems rather silly to do this because, first of all, if you have solar energy on your house, you're already renewable energy, right? So there's no point in buying energy from someone who's, doing renewable energy. Their price is almost twice what West Penn Power's price is. So for the most part, there's really no competition here. So the competition that we have is actually strangling the utilities. And I don't really know how to fix that. I mean, that's actually a policy problem that we have in the state. The solar energy does save lots of money, and it saves consumers lots of money, and it saves the suppliers lots of money, but it's the people receiving the savings are not necessarily the people who are paying for the expense, right? So here's the 4 different categories of people who I can say. They're solar customers. These are people who made the investment to switch to solar energy, so they actually put a lot of money into this, and they're kind of happy because they're not paying bills anymore. But that's a kind of a very close economics about whether it pays for itself or not. You see suppliers, all those 83 other companies out there, they're receiving huge savings, and in order to stay competitive, they have no choice but to pass those savings on to the consumer. If they didn't pass those savings on to the consumer, then they would become non-competitive to the other suppliers. So they receive the bulk of all the market suppression savings and turn around and pass those savings on to regular customers. So regular customers see a huge benefit. It's the utilities that we should show a very thin line of market suppression going from here up to the utilities, a very thin line. That line is probably not enough to offset the added cost of what utilities are actually seeing. And so utilities are kind of understandably down on solar energy. The problem isn't that solar energy is costing utilities money. The problem is that solar energy is benefiting perhaps other people who don't necessarily pay to the utility, if that makes sense. And so we need, basically, we need some new policy that maybe shifts these savings from the supplier over to the utility, or shifts money from the regular customers over to the utility, that basically so that the utility who's bearing the burden of paying the cost for having increased solar RPSs, energy storage, all that kind of stuff, that they receive some of this savings that's out there. There's a huge amount of savings that solar energy is generating. It's just perhaps not going to the people who perhaps need it. With that said, it turns out that about 50% of all customers out there choose their supplier, and you go on the market and actually choose their supplier. About 50% of them stay with the default supplier, in this case with West Penn Power. So if that continued, but that number's been going down through the years. If that number were to continue, then this market suppression, about half of it would go there and about half of it would go here, and the utilities would be happy. But they see that number going down through the years, so it's understandable that they're a little worried about that. So I think I will stop there. Perhaps I actually skipped right to my conclusion and policy recommendations as I gave that graph. Do you have questions?
Yeah, so thank you very much.
Oh, I do have to give this disclosure. So I own a solar company and deal with this. And actually, I also deal with one of the things that would actually solve this, and I try not to talk about it too much, is what we call SRECs, which are a way to shift some of those savings over to the people who need it. And I actually deal with a lot of SRECs, so I have to give this as a disclaimer.
So a question for people who are developing new solar energy projects.
Yes.
Is there some way that they can be taking advantage of this, trying to monetize this benefit in the project development process?
Utilities certainly do. I would say that the easiest way to do that would be at the industrial level. So suppliers would invest in solar energy because suppliers see that market suppression. I mean, they're first and foremost the people who save the money from the market suppression. And so, yes, if independent suppliers were to invest in solar, it would literally come back to them, double fold from what it would come back to anybody else. And I think we do see that happening right now, that the biggest players with solar energy in the country as a whole is at the industrial level. It's utility, the utility level. So I think those are people who are seeing this as savings, and that's why they're doing it. But I don't think that was your earlier question. I think your question was, can homeowners somehow leverage this, or can businesses somehow leverage this? And the answer is no, not really. It's blocked out from them. And in fact, the only way that there is a way in the market to, someone who develops solar is causing this market suppression to go on. So you would think that they should be the ones who benefit from it because they're the ones who caused it in the first place. And we have a mechanism in place to do that, and that's called solar renewable energy credits. But solar energy renewable credits, the SRECs, are selling for such small amounts of money today that it doesn't even come close to paying for what it should to get that suppression savings back to the person who created it. If it was the price, I have run numbers on what the price would be. The price would be about $150 per SREC. We haven't seen those prices in Pennsylvania in a long, long time. So I think not currently. There's just not a way to get those market suppression numbers back to the people developing solar energy. So solar energy is limited in Pennsylvania to just becoming economic based on just the net metering process. And if it's economic based on just the net metering process, then people go forward with it. And if it's not, then people don't. Yeah.
Not too long ago, the utilities were trying to attack net metering.
Absolutely. Well, they still are in many places, yes.
And, is this as a result of this imbalance that they receive from this?
I think in some places they perceive an imbalance. I will say that this was research in Pennsylvania. I got interested in doing this because I was in Wisconsin, where I was able to hear from a utility president from Minnesota who was speaking about his relatively small utility. It was, I think, the smallest public utility in the nation from what I recall. And he was talking very much about the challenges of solar energy. You can read that to be they didn't like what solar energy was doing at all. But they were in a market that their highest demand prices didn't occur during the summer like they do for us. Their highest demand prices were like, I showed that cold winter. That's what they get on a regular basis. That is what they get all the time. And so they actually had a legitimate beef. But that's when I got interested in running the numbers to see, well, could that really happen? Because I was kind of questioning whether that actually made sense. And that's what inspired me to do the research here. And then what was the rest of your question?
Well, I guess, so that's just one part of it, but I guess, so you have specific policy recommendations to somehow close that loop?
Yeah, utilities need to basically back up that when they say solar energy is causing them a lot of expenses, they need to back up what those expenses are and actually give some numbers. Because as it turns out, most customers, certainly commercial customers who have solar energy, they're still paying the utility. Almost every dime that they would have paid the utility beforehand, they're still paying the utility. I speak with a lot of, because I actually have a business that does this, I speak to a lot of commercial customers, potential customers, and they're a little bit, downbeaten about this because when they look into solar and they realize they're going to make a big investment in solar, and then they find out it doesn't actually do away with their electric bill, that they're still going to pay all those distribution charges, they get a little upset about that. And but yet that's a great scenario where the utility has no leg to stand on because they're getting all that they're getting all their money, no matter whether this person has solar energy or not. It's the residential consumer that they're not really getting that money for. Oddly enough, even at the residential level, if you could have, if you know what a time of use meter is, I'm in the Penelec area, and I actually have a time of use meter at my house. And Penelec has just changed their rules that if you have solar energy, you can't have time of use metering. And because they finally figured out that the reason I got the time of use meter was it was finally able to account for the daytime kilowatt hours as being more valuable than the nighttime, and indeed that's when they charge more, as being more valuable than the nighttime. And so that made sense, and that was more closer to what their billing process was. And they realized that I was actually able to get I would call it my fair share, and they said I was probably abusing their billing system. So they now took that away. And so I find that very ironic. Yes.
Can you explain a little more, if I understood it correctly, when you talked about the bidding process, everybody gets paid the same amount regardless of how much customers use.
Right, yes.
Why is that? Why isn't it just set up to give a certain percentage of profit above what they are going to cost?
People have talked about that as being a better model, but that is just not the model that we use in the bidding process that we use. I guess it's just not the system we have. That's maybe the easiest way to answer is that's simply not the system we have. I will also say that what people bid is not necessarily what it costs them. They, like a nuclear power plant nuclear power is quite expensive actually, but a nuclear power plant will always be the low bidder because they want to operate no matter what they want to operate. And they count on the bid not being what they bid, but they count on the bid being some higher number. So there's a lot of bidding that goes on where people aren't bidding what their actual cost is. They're bidding based on whether they fundamentally want to operate or whether they don't want to operate. And so they bid low or high based on that. And then it's all the people in the middle who bid, not low numbers, but reasonably high numbers. And they're the ones who are perhaps really bidding what it costs them. They're actually saying, I'll turn the plant on if you're going to pay me enough money, but otherwise I'm not, you know. So the bidding process is a lot more complicated than just that being the cost. Yes.
I had a small question about, so you said if some companies using solar power, then their costs would decrease. Like
Yes.
but then does that include also investment costs into solar panels or all of the need for solar energy to be produced?
Yeah, the investment that they make, every company is going to, you know, figure out whether their investment is worthwhile, you know, based on their savings that they're going to achieve. But yeah, so every company is going to be a little bit different because every price is going to be a little bit different. But they basically they're not going to pay the utility company, and instead they're, I don't know, paying a bank or an investor, whoever, you know, somehow paying off the investment that they made. But I would say that they must be happy with that, because if they weren't happy with whatever that was going to be, they wouldn't have made the choice to make that investment in the first place. I don't know if that's your question or not.
I guess what you're saying is that the analysis that you did
Yes.
does not take investment costs into account, but assumes that the company already has solar.
Oh, okay, yeah. So actually what I did is we measured the solar. Actually, we couldn't even measure all the solar that's out there. We could only, because there's no way to actually monitor all the solar that's out there on an hourly basis. You know, a lot of solar arrays don't even have any monitoring systems on them at all. So what we did is we could only look at the solar monitoring that used a particular type of inverter. And so it was all in-phase equipment. And that was basically something that we could data mine, that it was possible for us to data mine. We tried to data mine other stuff, but we never could basically get permission to data mine it, or it wasn't publicly available. And so that was something that was publicly available, and we could data mine it. And then what we did is we could also get information. We do know where all the solar is, so we're able to then scale what we can monitor up to where we know solar production really is in the state. And so we just scaled that up, you know, put in a scaling factor. And but to do the market suppression, we had to take that number, which is 0.15%, and we had to make it much higher. And the reason we had to make it much higher is the pricing that we see on the day-ahead bidding is based on the assumption that we have 0.15% of solar already out there. So people who are bidding, they already know that we're going to get a certain amount of solar energy. The people who are doing this bidding, they know exactly how much solar is already out there in Pennsylvania. They know the weather, so they know exactly what that's going to do to the market tomorrow. They already know that, so that's already priced in. So we had to look at what would happen if we took something that wasn't priced in yet. And so that's where we ramped up the amount of solar to a much larger number that's not already priced in, and then we figured what impact that would have on the price.
All right, terrific. Thank you very much.
Sure.
This brings us to the close of our seminar. Those of you who are registered as students for the seminar, please be sure to take part in the online discussion this week. And we will meet next 2 weeks from now for our next seminar. So thank you very much, everyone. And hope you have a great afternoon.
Thank you.
Thank you.